For Dr. Andrea from the Royal Netherlands Meteorological Institute. He's the one to take credit for all the work I'm about to present, and I hope to do justice to it. So, the objective of these studies were to investigate the interaction between thermally driven winds and urban climate, employing idealized simulations at the mesoscale. In particular, the focus is on understanding the impact of along city valley location on thermal comfort and air quality, to quantify the impact of urban morphology on thermally driven winds, and also to understand the physical processes of the interaction between valley winds and cities. The simulations used for this study are idealized and use two different scenarios, an urban and no urban one, with the following domain configurations. There's one way to nested domain. The bigger one has 3 kilometer grid spacing, and the innermost one has 1 kilometer grid spacing. As you can see, there's a big difference in size between the outermost and innermost domain, and this is to avoid boundary interference on the innermost domain. The idealized Alpine valleys are represented as 2 mountain ridges, and the 7 cities are located within and south of this valley. And this slide summarizes the model setup. So the idealized valley is located at a latitude of 46 degrees north and 11 degrees east. 2 different PBL schemes were utilized. The key K epsilon PBL scheme for the non-urban scenario was utilized because the author found that the bullock didn't perform well during the nighttime stable boundary layer, which instead the bullock scheme was utilized for the urban scenario. And then the urban canopy was represented by the backbend urban canopy multi-layer. And the urban fabric was represented by cities having by 13 by 5 kilometers in size, constituted by buildings represented by cubes of 15 meters size. In addition, there was also a constant release of tracers from the center of each of these cities to investigate the impact on pollutant dispersions. So these 2 maps represent the daytime on the left-hand side panel of the figure and nighttime mean wind speed velocity in these idealized simulations. As we can see in this is the no-urban scenario. So we can see that during the daytime there's a strong up valley flow, that is a southerly flow, that is almost negligible in the open plain outside of the mountain valley. But at nighttime, the situation reverses, and there's very weak wind within the mountain valley, while there's a strong northerly katabatic flow in the open plain south of the valley. So how does this wind impact the urban heat island of the 7 cities used as case studies in this research? So, contrary to what one would expect, the cities located let's say, south of the valley, so the D1, D2, and D3 represented by the brown, gray, and pink lines in this time series, exhibit the strongest urban heat island magnitude, despite experiencing a strong wind during the nighttime. Instead, all the cities located within the mountain valley experience a lower urban heat island during the night. This made the author think that probably the daytime wind is more effective in removing heat from the city, and so in modulating the urban heat island effect. This hypothesis is confirmed by these scatter plots. So the left-hand panel represents correlation scatter plots between the nocturnal wind speed and the urban heat island intensity for all 7 cities. And we can see that there's very poor correlation between the nocturnal wind speed and the urban heat island intensity, especially for the 3 cities located south of the mountain valley. Instead, if we look at the similar correlation scatter plot, but this time comparing diurnal wind speed and nocturnal urban inclination intensity, we can see there is a strong correlation between the diurnal wind speed and the nocturnal urban heat island intensity. Next, how do the cities uh, conversely affect the wind speed within and outside of the mountain valley? So here we are looking at along valley cross sections of daytime wind speed, um, and the black dashed line represents the wind speed in the no urban scenario, so without any city interfering with the wind flow. And we can see that near the surface, at 2 meters above ground level, all the cities exert like a drag effect on the wind speed, but especially those located within the valley. So we see a correlation between wind speed and drag effect. Also because the cities located outside of the valley can reduce the wind speed, but can also induce a sort of inward advection towards the city center. Above the canopy layer, at 37 meters above ground level, the situation is the same. And so for the cities that experience a strong wind within the valley, there's a purely mechanical effect that exerts a strong drag on wind speed. While the advection towards the inner part of the city extends even above the canopy layer. If we look at the nighttime valley winds, we see that there's no more advection effect, and the impact of the old cities is that of reducing the wind speed with a strong reduction in the order of magnitude of 1 to 2 meters. And that's especially true above the canopy layer. And again, this is correlated with the strength of the wind speed. So in this case, there are stronger wind speed reduction for the 3 cities that are located outside of the wind valley in the open plain, while the cities that are located within the valley that experience a lower background wind speed exert sort of a lesser drag effect on the wind flow. So finally, let's look at the impact of this interaction between thermally driven winds in complex terrain and urban environments on the dispersion of pollutants. So here in this figure, we see the tracer concentrations for a release happening both within the city, and that's represented by the red lines, both under and over the canopy, the urban canopy, and also the evolution, the time series of the concentration, the tracer concentration for a release that is 13 kilometers north of the sampling site, which means like the next north city. So the dashed lines represent the tracer concentration for the no-urban scenario, while the solid lines represent the tracer concentration for the urban case. And we can observe that during the daytime, the concentration is relatively low in case of a central emission, because this time the wind is southerly, so it is directed north. So most of the pollutants, most of the tracer is brought away from the city. The situation changes around 22, like 10 p.m. That's when the flow reversal happens. So there's a spike in tracer concentration, especially under the canopy layer. But although with a lesser magnitude, also over the canopy. The situation changes during the nighttime, where we have a reversal. So the tracer released by a city immediately north of the sampling site, is advected towards the sampling city. And so we can see during the nighttime an increase in the tracer concentration, which is for the urban case higher compared to the non-urban case due to the drag effect exerted by the urban environment. This situation propagates similarly upward over the urban canopy, And in the next slides, we're gonna look at sort of slow motion animation, which probably will make this interaction more clear. So this the animation starts at noon when the wind is anabatic, and so the tracer is advected away from the sampling city. The green line here represents the boundary layer, and the green arrows represent the wind vectors. So this situation keeps being steady with the tracer advected away from the city until we approach again 22 p.m. where flow reversal in approaches. We are in transition here. And so the flow now becomes katabatic and is advected, the tracer is advected towards the sampling side, towards the city. Here we start seeing the first differences between the urban and non-urban scenarios because the drag effect exerted by the urban environments slows down the wind and increases the concentration of the tracers near the surface. This situation keeps existing throughout the entire night until, again, the flow reverses and we go back to the initial situation. So to conclude, the urban Italian effect strongly affects the valley wind and depends on the position of the city within the valley. Valley wind's reduction depend on the increased roughness introduced by the urban environment and depend on the nocturnal temperature gradient. Temperature gradients are also relevant in terms of air quality because mixing can reduce tracer concentration within the urban canopy layer. And again, tracer concentration strongly depend on the coupling between roughness, temperature gradients, and basically the dynamic interaction. With this, I conclude, and I'll try to answer any questions, but if I'm not able to, please, this is Dr. Zonato email. Feel free to reach out to him if you have any questions I cannot address. Thank you.
Thank you very much. Do you have any comments or questions on this? Yeah.
I'm so glad that your talk was just after mine because you can clearly see the wind direction change matters, and then you basically see the idealized simulation. The knowledge of the like complex topography here because the downhill wind, up valley up slope and down valley down slope wind basically is governed by the temperature difference, correct? That's basically the main driving factor on a cloud-free day.
And the slope, yes.
And the slope, right? And that slope also go to the temperature there. And that is what I was thinking because is it like a feeding the chicken egg problem or not? Because because temperature gradient changes the wind and wind changes the temperature again. Can you comment on that?
Yes, definitely it's a complex issue that has also been, in my opinion, under-investigated so far. Spoiler alert, I'll also give another talk in 20 minutes more or less where I keep looking at this issue but in a realistic case. And yeah, I don't want to spoil too much, but there's a lot of research to do, but I found that heat fluxes, especially sensory fluxes, are involved into these dynamics and can change the way that this operates.
Thank you.
You're welcome.
Maybe I have time for one quick question, if it is a quick one. Otherwise, oh, you have one.
Just a very quick
Yes.
one. You showed the dependency of the heat island on the depends on where the city is located. Did you compare this to real city heat island?
In my knowledge, Dr. Zonato, I don't know if he did that, but yes, basically the talk I'm going to present later is about a realistic case.
Okay, great.
Thank you very much again.